Hello everyone, I'm Wanqi. We are Group 11 and our topic is Cangjie-AI GAN-based model creates new Chinese characters. Our project is related to image synthesis. We apply the techniques of generative adversarial network to train a learner called AI Cangjie for the creation of new Chinese characters. The name of the learner Cangjie is derived from a famous mythological figure who is memorized by Chinese people for inventing the earliest Chinese characters. The goal of the project is to train a model that generates fake Chinese characters that look just like the real one. I will introduce the data collection process and the challenge of the algorithm along with the solutions we proposed next. We collect 3,717 real Chinese characters from Xinhua Dictionary as the training data. We then use payload library to change the characters to pictures that can be coped with more easily. And the main part is the challenge of grappling with the data. We will compare our dataset with a classical dataset MNIST to illustrate the challenge that our unique dataset brings. Firstly, the amount of information of our dataset far outweighs that of MNIST, such as the components in Chinese characters. The complexity leads to a much poorer performance than the GAN gives in learning and imitating digital numbers. What was DC-GAN, the advanced version of GAN model, also performs badly on our dataset. The second problem is that we need to create new Chinese characters instead of imitating existing characters. What's more, due to the limited number of existing Chinese characters, the training set of our algorithm is relatively small and can't be augmented. Aiming at the challenges mentioned above, we come up with the following solutions. Firstly, use WGAN with gradient penalty instead of traditional GAN and DC-GAN. My teammates will explain in more detail later. Secondly, we increase the size of a single image from 28 times 28 pixels to 224 times 224 pixels to accommodate the rich information the characters contain. Lastly, we decrease the batch size in the training phase for the sake of a limited data set. My partner will introduce the following part.
My name is Yiqin, and I'm going to talk about the models that we use. The first model is GAN. GAN is a method of unsupervised learning that involves learning two neural networks play against with each other. GAN consists of a generator and discriminator like the plot shows. The generator takes random samples from latent space as its input, and its output will need to mimic the real samples in the training set as much as possible. The input of discriminator is the real sample or the output of generator. The purpose is to distinguish the output of generated network from the real sample as much as possible. So the final purpose of the two against each other is to make the discriminator unable to judge whether the output of generator is true or not. The discriminator outputs a value dx indicates the probability that input x is real. The objective of discriminator is to maximize the probability to recognize real image as real as generated image as fake. So the objective function is like this form, where PR is the real data distribution and PG is the generator distribution. And on the generator side, the objective function wants to the model generate an image with the highest probability value of dx to fool the discriminator. So theoretically, the generator of GAN should minimize the expectation of 1 minus log dx. However, it is unstable training. So in practice, the objective function generator is maximize expectation of log dx. Now I'm going to talk about the next model, which is the DC-GAN. The DC-GAN is a combination of CNN and GAN. The principle of this model is the same as that of GAN. It expects that the generator and the discriminator are replaced by two convolutional neural networks. The DC GAN makes some changes to the structure of convolutional neural network. The first is replace any polling layers with strident convolutions and fractional stride convolutions. Second is use batch normalization in both the generator and the discriminator. The third one is remove fully connected hidden layers for deeper architectures. Fourth one is use ReLU activation in generator for all layers except for the output, where the output uses the tangent edge. The last one is use leaky ReLU activation in discriminator for all layers. The following models are WGAN and WGAN with gradient penalty, where GAN is powerful generative model but suffer from training instability. Generally, if a discriminator is well trained, it should have a great effect on the improvement of generator. But in practice, it's just the opposite. If discriminator model is fully trained, the generator will even become worse. So the solution is to replace the Jackson channel distance with the Western distance. That is WGAN algorithm. Compared with the original GAN, the parameter of the new algorithm are less sensitive, and the training purpose is smoother. The network of WGAN is almost as the same as GAN, except the critic, which is the discriminator in WGAN. It does not have an output sigma function, and the major difference is only on the cost function. The critics of WGAN maximize the following function. Where fx is the critic function represented by a neural network, and the generator of WGAN is minimize the expectation of the critic function. WGAN with gradient penalty is an improvement of WGAN. It uses a gradient penalty instead of weighted clipping to enforce the resistance constraint. This simple improvement makes training process more stable and generate higher quality results. Now, my partner will talk about the following part, which is the experiment.
Thanks for the introduction of my partner. I'm Qiri, and now I will introduce the performance analysis part. Firstly, let me talk about the loss value. We totally trained the model for 22,000 turns, and here are the chain of the discriminator and the generator loss value. There are some interesting observations. In the first 1,000 turns, both two values change a lot. Then the D loss becomes stable, but G loss kept decreasing until around 4,500 turns and began increasing too. Around 10,000 turns, two values become balanced. For the rest of the part, we do not see an adverse change. The chain of the loss value also reflected on the output of the model. In the beginning, the output is meaningless. Although the model has learned the first component of Chinese character early, the output still doesn't make any sense. Around 4,500 terms, but the model has learned some more complex structure. Around 10,000 terms, the output is more similar to the real character, and we can see that the last two outputs are almost real with a little dirt. Our model did generate new characters and complete the mission of our project. Mainly, we can divide these fake characters into two classes. The first class is the real existence characters, such as this. It is funny that these characters only show once from 3,700 characters, but the model still successfully learned it. The second class is the model creation characters, which also are the mission of our project. And there are three examples. You can go to check that these characters do not exist in any dictionary. So what our model has learned from the characters dataset, we think there are at least 4 points. The first one is the components, which are the most common and frequent parts of the characters. The model can draw a very clear and accurate component but may be confused in another part. The second thing is the structure. Based on the historical output, we can find the order of how the machine learns the character's structure. The model only used 200 terms for the horizontal structure, but spent 4,000 terms for the vertical structure. And it takes 16,900 terms to learn the first single component characters. We'll talk more about this later. The third one is the handwriting. The model learned the style of the font we use to generate data, such as the parse writing. The last one, which is the most important thing, the combination of the components which let the machine generate the fake characters. For example, this one is the combination of Chinese character ZHOU plus the ZHOU radical. Now we move to the evaluation part. We rewrite our fake characters to clean and normalize them with other real characters and hand out the questionnaires. The questionnaires ask respondents the following question. Every group has 1 character created by AI with 3 real used characters. Please try to choose the fake one. And here are 3 groups as the question in our questionnaires. We totally recovered 84 questionnaires. The result has shown in the following bar charts. Only 90% and 24% of people picked the correct one in Group A and Group C. So we can see that 2 of 3 fake characters successfully confused the respondents, which show a great performance of our model. On the other hand, there are also some problems with our model. The first one is instability. These are 2 characters we show on the previous page, but their adjacent output are not good enough. In fact, around 8% to 10% of outputs are clean enough and understandable. The second one is the dirt output. The characters always are generated with some noise. We try to clean this noise by image processing, such as the function in CV2, but it will decrease the quality of the picture. However, please look at the left part of this one. The model has the potential ability to give a really clean result like this. The third one is the limited creation ability. Although our program did generate the new characters with the combination of current existent components, it's hardly to create a really novel character with new components or structure. Actually, it did create some new components, such as the one shown in the graph, but based on some reasons, it fails to develop it furthermore. We also provide some ideas for potential improvement. Firstly, we can set decay for random noise and email it to a cleaner result. Or we can keep increasing the training time. Maybe 22,000 turns are not enough for our project. Moreover, we can add some labels, which may bring a positive effect to the model according to some research. So let me move to the last part. What are the meanings of our project? Firstly, we provide a machine vision or a mathematical vision to understand Chinese characters. People learn the single component character as the starting, but it is difficult for the machine. And these records may help the studying of the Chinese characters. Recall the performance analysis part. The model can learn handwriting style, and it may help people develop their own font by adding the style transform into our model. At last, these fake characters may be used in some fiction novel or video game. Here are our references. Thank you for your watching.